Assalamu alaikum, dear students. I'm very happy to be back with you with another video lesson. In the previous video lesson, we talked about mutual inductance, and simply we said mutual inductance is the creation of voltage, is the creation basically, or the ability of one circuit, let's say, to induce an electromotive force of voltage in the other circuit. And of course, we used to call one of the circuits primary circuit and the other one is secondary circuit. And of course, remember this, as long as there is a change, or you can say this happens in the presence of a changing current, because remember this, if the current does not change here, the magnetic field around this coil, let's say, it is not going to change. And if this doesn't happen, then of course there's no change in the magnetic field. You can say there's no change in the magnetic flux as well. And if that is the case, then of course there will be no induced electromotive force. It is as if, let's say, there is a magnet or permanent magnet, let's say, brought close to one of the coils, let's say, and that's it. There's no more movement there. And if that is the case, then of course there will be no more or no induced electromotive force. And that is simply where the mutual inductance is. And of course we did say that basically, we did say that this act or this process, of course, is going to induce electromotive force. And once again, the base of this, you can say it is electromagnetic induction. The reason why electromagnetic induction, because there is a change in the magnetic flux of, let's say, one coil, and of course this will, let's say, induce a voltage, let's say, and of course this voltage will lead to a current in the other coil here. And of course, by the way, we can increase or decrease the voltage that is induced depending on, let's say, various factors. And of course, one of them, let's say, the number of turns, you can say, or let's say the iron core that we're using, let's say the shape of the coil and all that. So there are some factors that of course depends on, let's say, or the magnetic, let's say, electromotive force that is induced, of course it depends on. So, and I've also mentioned that, that the electromotive force equals to N, that is basically the change of the magnetic flux, you can say, divided by the time, which is of course the same or equal to negative M multiplied by the change in current divided by the time. And of course, and we said that M is basically called mutual inductance and it is measured in Henry. Okay, now what does the mutual inductance depend on? All right, we've also covered that as well. We said the geometrical property of the coil, and of course that is basically, let's say, the orientation of the coil, the number of the coil, the magnetic permeability, and all that. Yeah, so these are some of the factors that this, of course, it depends on, which you can call it the geometrical property of the coil, and of course also the orientation of the coil to one another, and of course perpendicular or parallel to one another. And of course you do know that we get maximum electromotive force that is induced if the two coils were parallel to one another, and if the, of course you can say minimum or zero if once they are perpendicular to one another. So we can say, if let's say these are the two coils, if these are, let's say, parallel to one another, like this one here, of course you get maximum induced electromotive force. And of course, let's say if it is something like this, these are, you can say, sort of perpendicular to one another, of course you can say you get minimum electromotive force that is induced over there once they are perpendicular to one another. Okay, so now another thing that we've also mentioned was this. We said the induced electromotive force in the secondary circuit can be changed by changing the number of turns of the wire in the secondary coil. Okay, and of course we said this arrangement is the base of an extremely useful device or electrical device that is called transformer. And by the way, by changing this, of course, or by changing the induced electromotive force, what is the importance of this device that is this so-called transformer? Yeah, and of course transformers, you can see that if you look around, of course there are a lot of transformers, starting with the let's say your cell phone charger, let's say, or it could be a laptop charger, it could be any other electronic device, for example, that has it has a transformer in it where, for example, the voltage of the mains, or let's say the main voltage is too high, let's say, for this electronic device. So this transformer, of course, is going to lower this voltage. So of course this transformer, it is a device that it can lower or let's say increase the voltage, but of course not from out of nowhere, of course, by increasing or decreasing the current. Okay, so just remember this. By changing the number of the turns, of course, we can increase or decrease the voltage that is induced here. So we have another question, says, what is the basis, or what is the base or basis of work of transformer. We said it is electromagnetic, or by the mutual induction, of course, yeah. And of course, this mutual induction is based on the electromagnetic, you can say, induction as well, because there is a change in the magnetic flux. But why mutual? Because you need two coils in order for this to happen, not a permanent magnet for this, yeah. So of course, that is basically what is called mutual induction. All right, so remember we said using two circuits, or you can say using one circuit to produce electromotive force in the other circuit by the presence of changing of electrical current. That is what is called mutual induction. It's like you need, of course, to have at least two coils for this to happen. So once again, mutual induction we can say, or mutual inductance equal to negative electromotive force divided by the change in current divided by the delta time, you can say. And we can define it this way. We can say it is the ratio of the induced electromotive force in the secondary coil, by the way, because this electromotive force that is induced is going to be induced in the secondary coil, because we do have, or you can say the primary coil is connected, let's say, to a power supply, to, let's say, a power source, let's say, yeah, whether this power source could be the main current, could be a battery, could be any other sources that could provide the electrical energy for the first coil. But the second coil, it is the one that induces, or let's say uses this change in the magnetic flux into, let's say, induced electromotive force, which we can say it is the ratio of the induced electromotive force in the secondary coil to the rate of change of current in the primary coil. Okay, and of course we stopped right here. We said describe how mutual induction occurs, yeah? So of course, so far, I hope you have an idea how mutual induction or inductance occurs. We can say mutual induction occurs when there is a change in the current in one coil, that is mainly the primary coil, which creates a changing in the magnetic flux, and of course, which increases, or you can say induces an electromotive force in the nearby coil secondary without a direct electrical conduction. So of course we can say this. By the way, we can say we have an electrical current. That is, this electrical current, of course, once it is increased or decreased, it will have, let's say, a change in magnetic field. Yeah, this change in magnetic field, of course, you can say it leads to a change in the magnetic flux. Okay. By the way, because these magnetic field lines are going to be, let's say, crossing at right angle to the cross-sectional area of the other coil here, and of course, this one here, of course, is going to induce an electromotive force. This electromotive force will also induce a current in the primary coil here. Okay, and of course, you can say these are all for, you can say, or this two-part, let's say, of course, for the primary coil, and of course, and this, or having these magnetic fields over the cross-sectional area for the second one, that is going to be the second coil, and then after that, this would induce a voltage, and this voltage would lead to an electrical current flowing through the circuit. Now we have a question here. It says a pair of adjacent coils has a mutual inductance of 1.06 Henry. Determine the average electromotive force induced in the secondary circuit when the current in the primary circuit changes from 0 to 9.5 ampere in a time interval of 0.0336 seconds. And of course, the idea is pretty simple here. You just plug the numbers into the equation, and then of course, that is all you need to do to find the answer here. Okay, so let's do this together. All right, remember, it says what? It says find, it says find what? I forgot, where's the question here? Okay, so determine the average induced electromotive force in the secondary. So we can say induced electromotive force equals to what? We said that equals to negative m, that is basically delta I over what? Over delta t here. So everything you need is already there. So electromotive force that is induced here equals to negative, that is 1 point, let's just write this one nicer. Okay, equals to 1.06, that is in Henry, don't forget, multiplied by the change in current. That is basically final minus initial, yeah? So it starts from 0 to 9.5. This is, we can say I2, which is basically 9.5 minus 0 divided by the delta t, which is 0.0336 seconds. And of course, you do the math, you will get the answer. But of course, it has to be negative because you can see that this is basically opposing the change in the external magnetic field, you can say, or just negative to make it short in here. Okay, so this is how it is done, mainly. It's very simple. All right, now take a look at these Wrya questions as well. It says the ability of one circuit to induce an electromotive force in the nearby circuit. That must be very obvious to you. And of course, in the presence of a changing current, that is mutual induction, because remember this is, okay? The ability of one circuit, all right, in the nearby circuit. So of course it has to be mutual induction, which is in this part going to be part B. Okay. Now the second question says the symbol M in the in this equation. What does it stand for? What does it resemble? That is, of course, you can say mutual inductance. All right. The mutual inductance between two coils depends on what? Okay. Something also very important. What does it depend on, guys? If not, you can just remember the equation. That's one thing, and of course, yeah. So does it depend only on the geometrical property of the coil? No. Only on the orientation of the coil? No. We'll say both the geometrical property of the coil and their orientation to one another. So of course the answer is going to be C. All right. Now there's another question. It says a pair of adjacent coil has a mutual inductance of 1 Henry. What is the average induced electromotive force in the secondary circuit when the current in the primary changes from 0 to 9 in a time interval of 0.03 seconds? So this is pretty much the same as the one that I have just solved. You just write the equation, plug in the numbers, you'll find the answer. Okay, now we have section review. Says what? A loop with 37 turns and of course an area of 0.33 meters squared is rotating at 281 radians per second. The loop's axis of rotation is perpendicular to a uniform magnetic field with a strength of 0.035 Tesla. What is the maximum induced electromotive force? We've learned that, okay? Let's get this one to the other side. Okay, let's get it here. So what is the, by the way, okay, we're basically trying to find the maximum induced electromotive force in here. Nope. Okay, so once again, all right, remember this. We have number of turns, which is basically that is n, 37 turns. And of course we have area, or let's say that is 0.33. And of course we have rotating at 281 radian per second. That is angular, all right, speed you can say, or angular frequency. That is also fine. All right, the loops, and of course the loop's axis of rotation perpendicular to uniform magnetic field, let's say, and B is basically 0.035 Tesla. So what is the maximum induced electromotive force here? If it was not maximum, of course, we would have said electromotive force equal to, let's say, E max, or electromotive force that is max sine, let's say, omega t. Yeah? But since it says maximum, so this part is going to be 1. The whole thing equals to 1. So all we have to do is maximum. And what is maximum equal to? It is equal to NAB omega, yeah? All right, very good. So we have number of turns, so just plug in the numbers. That is 37 multiplied by 0.33. Okay, 33. All right, multiplied by, that is B, which is 0.35, and multiplied by omega, which is basically 281. So you do the math, of course, you'll get the answer in volt, because that is maximum electromotive force, which, as you can see, that it is about 120 volt. Okay, now we have another question that's pretty almost like the same idea with the other one, a generator of all this. What is the question? The question wants the strength of the magnetic field in which the coil rotates. Yeah, so pretty much the same thing, but so we're going to, since we have the maximum voltage or electromotive force, we'll say electromotive force or maximum equal to NAB omega. Yes, so we are trying to find the strength of the magnetic field, so B equals to maximum electromotive force over NA omega, yes? And by the way, another thing here, if omega is not given straight, let's say, or directly, this omega equals to 2 pi f, and of course you're given the frequency, so in this case the frequency is 60, so 2 times 60, that is 120 pi. You can just write it here, and then you can find the strength of the magnetic field, or just the magnetic field strength. Okay, we have another question. Says, explain what would happen if a commutator were not used in a motor. We said one of the benefits of this commutator is basically reverses the direction of the current. So let's say when the coil is rotating, let's say here is the orientation of the coil, yeah? So the coil is making a full turn, let's say. So far the rotation is forward, okay? So now when the coil, for example, have rotated half a cycle, okay, in this case the direction of the current, let's say, of this coil, or you can say because of the magnetic field, let's say if it's fixed here, so in this case the direction of the current in the coil is going to be reversed, you can say, okay? So if that is reversed in this case, then we can say the current, okay, or you can say this rotation, of course, it's going to reverse or rotate in the opposite direction. So in order for this not to happen, of course, the commutator, which is two split rings, of course, it will kind of like reverse the direction of the current so that the rotation is always in one direction. That is, let's say, for a motor, yeah? Remember this. It is the same thing for a generator, let's say, if it is using or if it is DC generator, so that it can reverse the direction of the current so that it is always in the positive direction, you can say, or we always get the, let's say, positive part. Okay, but since it is a motor, of course, there is a rotation in one direction. Remember, the motor is basically, we're using electrical energy, converting that one to mechanical energy. So for half a turn, it will rotate. Then the electrical energy is about to, let's say, or the, what is it called? Because of the magnetic field, you can say, and the coil or the orientation of the coil has changed. So unless you change the direction of the current, otherwise the rotation will not continue in the same direction. So we can say mainly the job of this commutator to reverse the direction of the current so that the coil rotates only in one direction here. So without a commutator, the motor's current wouldn't reverse, causing a misaligned magnetic field and of course preventing the continuous torque, resulting in erratic or halted movement. So the movement is going to be like a little back and forth, and then of course there will be kind of like, or it doesn't, the motor will not work to make it short. Now we have another question here, says critical thinking. Suppose a fixed distance separates the center of two circular loops. What relative orientation of the loops will give the maximum mutual inductance? We've mentioned this one. What orientation will give the minimum mutual inductance? We've said that the maximum or the mutual inductance will be maximum when the two coils are parallel to one another, and of course the mutual inductance will be minimal when the two coils are perpendicular to one another. Okay, that was for this one as well. Now let's start with a new concept here, and that is 6.3. We're going to talk about AC circuits and transformers, yeah? But before we start with this one, of course, we're going to start with the effective current. Now, before talking about effective current, of course, perhaps you are familiar with this device right here, yeah? We normally have devices to measure, let's say, to measure the current, to measure the voltage, and to measure the resistance of a resistor as well, yeah? So, of course, we have different devices, yeah? To measure, let's say, the current, if it has a great value, of course, we're going to use an ammeter. If it's very small, we're going to use a galvanometer. For voltage, let's say, or potential difference, we're going to use a voltmeter as well, yeah? And of course, if it is a resistor, we can use ohm meter. That's something different. But we can have one device to measure all of these all together, let's say, but of course, each one at a time, not all together, and that is called multimeter, which is right what you see here. Okay, so the electromotive force in a circuit is analogies, you can say, to the potential difference in a DC circuit. Remember this? So instead of sometimes you will see that, like so far we've been, let's say, the induced voltage that was, for example, that we were inducing, of course, we used to, let's say, resemble or represent this for that, yeah? But of course, now we're going to use, let's say, voltage instead of this one, which makes no difference, you can say, yeah? So the electromotive force in an AC circuit is analogous to the potential difference in a DC circuit, we can say. So we have the resistance, let's say, we have the current I, there's the symbol for resistance, the current I, and of course, electromotive force, this one can be measured with a digital multimeter. That is this digital multimeter by choosing the proper setting on the multimeter and of course locations in the circuit, of course. You will see that here it indicates what? It indicates, let's say, this is the you can say, that is basically the neutral one, it goes here. And of course, for this one, if you want to measure the voltage, you connect it here. If you want to measure, let's say, the resistance or the current in milliamperes, if it is in small range, you will connect the wire here. If not, you can see this one would measure current, but in a range, of course, you can say 10 amps and above, you can say. All right, so these are not a big deal here, just a device that, of course, by, let's say, once you have this device, of course, you will get enough information how to use it as well. All right, but now we have something else. Effective current and effective electromotive force are measured in AC circuits here. So what are the effective current and effective electromotive force? All right, now, we can say that the electromotive force produced by a typical AC generator is sinusoidal, you can say, or sinusoidal, and varies with time. So the induced electromotive force as a function of time can be written in terms of the maximum electromotive force, and of course, let's say the EMF or the maximum electromotive force produced by a generator can be expressed as follows. Yeah. So of course, when we were talking about generator, for example, yeah, and of course we said this generator would induce, let's say, a voltage, yeah, and of course the voltage that was generated, we could have set it, for example, E max, right, or electromotive force max, and of course sine, let's say omega t, yeah. And of course now instead of this, we can write V here, or change in the voltage, you can say that is basically going to be instantaneous, by the way, because this is sinusoidal here. You can see that this value, of course, changes at every moment or every second here. Let's say this is V, and of course this is a function of time, yes? So you can see at a point it is 0, at a point here it is increasing until it gets maximum, then decrease to 0, maximum, but in negative direction and all that. This is sinusoidal wave, you can say, yeah? So of course, instead of writing this or all that, we can just write this instead. We can, instead of every electromotive force, we can say a potential difference or voltage here. So the instantaneous voltage, that would be the voltage at any second, at any moment, at any instant here, equals to the maximum voltage or electromotive force sine omega t here. Okay, now this basically, you can say the angular speed of the rotation, you can say. Sometimes can also be called the angular frequency, and then this is, you can say, the time as well. So sine is a function of this two here. Okay, now that'll be instead of angle theta, by the way. Okay, now the instantaneous current that changes with the potential difference can be determined. And of course, we do know that, okay, this if once this voltage is changing, of course, that leads to a change in current as well. So of course, we can say when the voltage is 0, what can you say about the current? And of course, that is also 0 here. So this one here, of course, we can write the same thing for, or you can say this current that is induced will also be sinusoidal here. And of course, this this wave, or you can say this diagram, of course, it represents the instantaneous current. So in another way, we can just write the current as, for example, as it mentioned in this equation, we can say the instantaneous current, we'll use this, I max, that is going to be maximum current sine omega t here. Okay, so the instantaneous current I is related to maximum current by the following expression, which you can see here. And of course, in a circuit diagram, the AC source is represented by this symbol here. And of course, we have different symbols, or we have studied different symbols so far, yeah? And of course, let's say this is what we're going to use, let's say, for AC source, let's say. But if it is something at DC, for example, we could use just the symbol of a battery, let's say, or cell, you could say. We could have one cell or multiple cells when you call the battery. All right, and of course, what else can we have, yeah? So these two would be the difference. This is DC and this is AC, and that's it for now. And of course, later on, we will have different symbols for this. Let's say this is going to be a symbol of a resistance, the symbol of inductance, let's say. And later on, of course, we will have the symbol of a capacitor or capacitance as well. And of course, these two are very similar to one another, so you have to be very careful. This one has a longer side, you can say. And of course, normally thinner than the other side, but that doesn't make a difference. Just remember that if it has one side longer, that is obviously a battery. And of course, if these two sides are equal and parallel to one another, that is more likely a capacitor. So remember this. The rate at which the electrical energy is converted to internal energy in a resistor, that is power, and has the same form in the case of direct current here. Well, basically now we'll be almost like talking about the difference between effective and effective current, of course, and a direct current as well. The energy produced by an alternating current with a maximum value I max is not the same as that produced by a direct current of the same value. The energies are different because during a cycle, the alternating current is at its maximum value for only an instant here. Now let me tell you what exactly this is about, yeah? So we normally have, we talked about DC sources, yeah? So if this is one of them, in DC, of course, we have, let's say, a fixed value of electrical voltage, let's say. So let's say if this is provided from a battery, and this value that we have, let's say it is 10 volts, so you get 10 volt always, constantly, yeah? And always, yeah? This is basically, you can call it a DC, okay? All right, and of course, let's say, what if it is AC, for example, yeah? If this AC is providing, let's say, or if the AC is 10 volt, let's just say, or we can switch this with 10 amperes if you want to, remember this. This is only, for example, let's say 10 amperes or 10 volt, let's say, okay? 10 volt only for an instant, only when it is maximum, yeah? Of course, you can see that these ranges are going to change right here. So, of course, now you can say that if it is a DC, provides with a constant volume, which is always the same, but if it is AC, okay, let's say AC and this is DC here, you can see that these values are changing. It is only maximum at an instant for only, let's say, a fraction of a second, or it depends for how long it is. Okay, now after this, we can talk about the effective voltage and effective current. So what would be the difference between the two, or why do we call it effective, yeah? Okay, we have a term, and that is called effective current, or sometimes we call it root mean square. Okay, so what is this? Now we'll say the value of the alternating current that gives the same heating effect as that, or you can say heating effect that the corresponding value of a DC or direct current does. In another word here, we say that or let's say effective current, it is a value, or you can say it is a value of the current that gives the same heating effect that a DC, or you can say direct current does. Okay, what do I mean, or what do we mean by this? Watch this one here. Let's say we have an electrical heater, or could be any other thing, yeah? All right, so I'll just draw one component of the heater, so not the whole thing, yeah? So let's say this is the heater here. That is basically heaters or resistors, you can say, yeah? And of course, they dissipate energy in forms of, let's say, or convert electrical energy to thermal energy here. So this is for, let's just say this is for AC, and of course, we have another one for DC. And of course, these are, okay, let's just continue this one since we're talking about this. So remember, one side negative, the other side is positive. That is a DC circuit, okay? And of course, this one is an alternating current, you can say, or an AC circuit here. So what does it exactly say? Now, because this one, or the value of the current is constantly changing, let's say from maximum to minimum to negative maximum and all that, let's say, so if the value here is 10 amperes, let's say, or maximum here, it is only, for example, 10 amperes for a fraction of a second. But if this battery provides, let's say, 10 amperes, it is going to be 10 amperes sharp, that is straight, or you can say straight or constant. It is always providing 10 amperes here. All right, so you can see here that this one, of course, is going to give, let's say, a lot more energy, or convert a lot more electrical energy into thermal energy, let's say, per second, let's say, compared to this one here, yeah? That's obviously because this value here, it is going to change from 0 to maximum, to 0 to maximum, negative, and then 0 again, yeah? So, but if we take an average or something for this one here, we will have something, a value, all right, that is going to be this one, or a value that is close to this one here. And if we take an average, so we can say an average, or the average for this one is going to be something, a value that is right at this point here. But if that is the case, let's just say this is 8 amperes, let's say, yeah? And if this is now 8 amperes, we can say, now this two value, all right, let's say this is 8 amperes as well. Now we can say this, even though it has a maximum of 10, but of course it has something else, you can call it root mean square, or effective value, that is basically 8 amperes. Now this 8 amperes basically gives the same heating effect as this direct current here. So I'll repeat this, yeah? We'll say this effective, or you can say effective current, it is basically a current, you can say, or a value of the current that gives the same heating effect as this DC current gives, yeah? But remember, this is for AC and this is for DC. But in order for this, of course, we can see that you can see that it is always less than maximum, by the way, okay? And of course, it is bigger than 0, which is, this one is basically, we're going to talk about this one, which is a little bit more than 2/3. It is about 70 point something. We'll talk about this one in a second here. Okay, but let's go through the definition one more time before we move on this. All right, so the effective current, root mean square volume, okay? And sometimes we just write I for, or E for short. Let's say effective voltage, effective current, or effective power, whatever it is, yeah? So we'll say the value of the alternating current. So we have an alternating current, but a value or certain value for that alternating current, of course, it is gives the same heating effect, you can say, that the corresponding value of a direct current does, you can say, okay? And that would be for that. So the effective current, a root mean square current, is the same as the amount of direct current that would dissipate the same energy in a resistor as as it dissipated by the instantaneous alternating current over a complete allotting equations. Okay, now we have a question here. It says, which quantities remain constant when alternating currents are generated? So, okay, so this is pretty simple to answer this one, because remember this, we said when current or voltage or when these are generated, of course, this is what we have, yes? So you can see here that let's say this is for, let's say this is for the current, okay? So this is what we have, yeah? So take a look here. When we have a maximum value, these are always constant, yeah? That's one thing. So we can say the maximum current that is generated or produced is constant. That is one thing, which is the same thing for the voltage, by the way. We can draw the same thing for the voltage, yeah? So we can say these are basically constant. That's one thing. What about, for example, the let's say the frequency, okay? Or you can say the rotation here. Of course, if it is going to, let's say, or the speed of, or you can just say the rotation here, or the frequency of the rotation, it is not going to change here. So for example, if this is, let's say 1 rotation, it still remains like this, and of course that is also remains like this one here. So basically the maximum values will always remain the same, and of course you can say the frequencies, which is basically the number of, you can say the rotation here per unit time, that is also going to be constant here. But other values, of course, you can say the instantaneous values are the ones that are going to change. Because, for example, you can say that we have 0, and then, of course, increase up to maximum, and then decreases to 0, then maximum negative, and then 0 again, and all that. Yeah? But these values are not going to change, but because these will always stay the same as they are. Maximum value, if it is 10, it's always 10, and so forth, and the same for the other ones too. Which, if these are, by the way, constant, then of course it makes the I effective also constant as well, because I effective equal to, we said it, maximum over the square root of 2, V effective, the same thing as well, yeah? But not the current, by the way. We'll say V max over the square root of 2 and omega, that is 2 pi F. All right, moving forward. We can say, there's another question here, says, how does the power dissipated in a resistor by an alternating current relate to the power dissipated by a direct current that has a potential difference in current values that are equal to the maximum values of the alternating current? We've mentioned that the power dissipated by the AC current, let's say, or by the AC source is going to be half of the power dissipated by the direct current when they are at maximum, let's say. Okay, so once again, we'll say the power dissipated, okay, the power dissipated in AC here, or that is going to be, let's just say the AC. The power dissipated in AC is going to be half of the power that is dissipated in direct current, let's say, or just DC. Okay, so once again, the power dissipated in AC is half of the power that is dissipated in DC. All right, now we have question 33. Says what? In a ground fault interrupter, yeah, that is basically devices when there is a fault in the circuit, or if, let's say, if current or electrical current, let's say, it is moving to somewhere else, or if the current, let's say, requires more current than it was supposed to, then this device can detect it, and of course, and then it can break the circuit. So in a ground fault interrupter, with the difference in the current across an outlet, they measured in terms of the root mean square values, the effective values of the current, or the actual current at a given moment. Explain your answer. And of course, we said that because the value of the alternating current is going to change constantly, yeah? So this is, let's say, increases and decreases. Of course, this device cannot, or it wouldn't be very accurate, because let's say, to measure the instantaneous current, because these values are going to increase or decrease, let's say, at every instant or at every second. So, but instead of this, it would be best, or these devices, you can say, it will measure the effective current here, because these effective currents are almost like a straight line. It's almost like a DC, a direct current that is always at a value. So of course, if this value, let's say, if more than this value needed or used, that means there is a fault in the circuit, and of course then the circuit will be broken, so that you don't get an electric shock, let's say, or you'll be saved at this particular time. So it is, or it measures, or it is measured in terms of the root mean value of the current, or you can say the effective value. This ensures a reliable detection of imbalances between the hot and the neutral wire, which is crucial for providing an effective protection against ground faults. Okay. All right, now we have another question. It says voltmeters and ammeters that measure AC quantities are calibrated to measure the root mean square values of electromotive force and current, yeah, respectively. Why would this preferred or be preferred of measuring the maximum electromotive force of current? And of course, when you look at a, let's say, a voltmeter or an ammeter, we want to look at a steady, a fixed number, for example. Let's say 10 amperes passing through this wire, yeah? If it is an alternating current, this is not going to show us 10 amperes, yeah? Maybe perhaps in a second it might give you, let's say, 100 times, let's say, not 100 times, let's say 50, 60 times, maybe it might show you, let's say, 50 degrees and then positive and 50 negative and all that, yeah? So we don't want that, right? So it is preferred to measure the root mean square value, let's say, or the effective values, so that we can have an idea, like on average, how much current is passing through this wire or let's say, this component that we have. So of course, or just to make it short, if it is instantaneous, these values are changing constantly, so of course it's not going to give us an accurate reading there. Okay, so it has to be root mean square values, or sometimes we call them effective. Okay, so we have a sample problem here. It says a generator with a maximum output of 205 volt is connected to a 115 ohm resistor. Calculate the root mean square potential difference, find the root mean square current through the resistor, and find maximum Imax AC current in the circuit as well. So let's solve this question together. So we have a circuit, and of course we have different values, you can see. Okay. All right. So now let's write the information that is given. So we have maximum output electromotive force. So we can say we have Vmax, which is about 205 volts. Okay, and then it's connected to, we have a resistor. This resistor, you can say, oh, not this one here. So the value of this resistor is basically 115 ohms. Okay. And then we have says calculate the terms or the root mean square potential difference. So find V root mean square. Another name for root mean square, you can call it effective, which is the same as V effective, yeah? Very good, find this. And then after that potential difference, find the root mean square current. So find I effective, you can say. And then through the resistor, and find maximum. And then after that, you can find I maximum as well. Okay. Now, so take a look what I have and then what I can find here. Now, so first of all, how can I find the V effective? I have Vmax, then I can easily find V effective. So we said V effective equals to Vmax, basically, Vmax over the square root of 2 here. So what is Vmax in this case? Vmax is basically 205 volt divided by the square root of 2. You do the math, of course, you'll get the answer in volt. We'll do it in a second, okay? Now, as for the second part here, says what? And then find the I effective. Remember, I have Vmax, let's say, and V effective. I found V effective, let's say, and then I can find I effective by using the resistance as well. So of course we said resistance equal to what? Equal to V over I. Remember, because I can use Vmax over Imax, but the question at this point here says find the I effective, yeah? So of course I'll use V effective because that is what I have, and then I can find I effective as well. So in this case, of course, we can say I effective equals to V effective over the resistance here. So whatever the V effective is over 115, then of course we can find the I effective. That is 2 so far, okay? And then the third one says find I maximum. Okay, so in order to find I maximum, we have I effective equals to I maximum over the square root of 2, correct? Yes. Now, if we want to find I maximum, of course you can cross multiply, so I maximum equals to I effective multiplied by the square root of 2. Now, using all this, of course, now you can find the answer. Okay. Now, of course, we can use a calculator, or we can get these numbers or these values, we can just plug them into the equation. All right, so let's see if we can do that. Not for this. Okay, so take a look. For V effective, it is 145. Okay, that is V effective. And of course, we get I effective 1.26. So 1.45 let's go to that. So we can say this is was it 1 point? And how easily did I forget? All right, 145. 145. Okay, that is basically in volt. Don't forget that is the V effective. Okay, and then of course we'll use 145 and then divided by 115. That is 115. Okay, and then let's just write this one nicer. And then divided by 115 here. Okay, and then of course you can get the I effective, which was basically 1.26. Okay, which was 1.26. And then finally 1.26, and then finally you can find I maximum, which is I effective multiplied by this. So in this case, of course, 1.26 multiplied by the square root of 2, yeah? And then of course you can find the answer that is going to be in amperes. And of course the answer was basically 1.78 amperes. Okay, and of course you can add an ampere here. All right. Let's just add an ampere to this one. All right, now next one, of course, or in the next session, we're going to start with practice 6C. And of course, after that, we're going to talk about, let's say, different circuits, or how we can, let's say, dive, let's say, into, let's say, the electricity more with these and that. Of course, we will have, let's say, circuits. If this circuit, for example, if it only has a pure resistance, how are we going to find, let's say, I effective, V effective, and any other values that were being required? Could be power, could be the energy, for example, or anything else. So till then, I want you to keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.